The largest cat to ever walk the earth is not the Barbary lion, the saber-toothed tiger, or the giant lynx. It is this guy, living now. The gene for growth is on the Y chromosome for lions and the X chromosome for tigers. When you breed a male lion with a female tiger, two animals that do not normally come in contact with each other in the wild, you get the largest feline ever, the liger. At over 12 feet and 1,000 pounds, there has never been anything like it. Sometimes the combination of two well-known elements will have unexpected characteristics. Hello and thanks for listening. The Terran Space Academy is dedicated to educating you for a bright future in the space industry. Don't forget to like and subscribe, and support us on Patreon if you can, at patreon.com/Terran Space Academy. We know it's hard for everyone out there right now and appreciate anything you can contribute. We just went over 1,000 subscribers, and I want to thank each and every one of you for your support. Now that we have over 1,000 scholars studying at the Terran Space Academy, it's time to come up with a motto. I propose, ad Astra Pro Terra, to the stars for the Earth. As the Earth can only survive the crush of human civilization if we access the riches of the solar system. Let me know what you think. Now on to superalloys. Superalloys describe combinations of metals that produce an alloy with unexpected strength, hardness, thermal resistance, or another useful characteristic. We see this all the time. None of the elements yttrium, barium, copper, or oxygen are superconducting at high temperatures, but the combination, while not an alloy but a ceramic, produces the high-temperature superconductor used in the SPARC reactor, as we learned in our lesson on superconductivity. We saw in our lesson on Starship Steel how copper and tin make the more durable metal bronze, while alloys of iron can make steel. And in the lesson on aluminum alloys, we saw that a combination of elements can produce a lightweight but strong version of aluminum that is vital to the success of the SpaceX Falcon 9 reusable rocket. Now we are going to learn about two alloys that have useful characteristics far exceeding those of the elements from which they are composed. The first alloy you need to know is called Inconel. This was one of the first superalloys discovered. Now remember that adding nickel to iron makes a strong steel alloy, and mixing chromium to iron makes the corrosion-resistant stainless steel. What if we leave out almost all of the iron and just mix nickel and chromium? Inconel is the trade name for an alloy with this combination, and it is one of the most useful superalloys discovered so far. One of the characteristics of most metals that limit its usefulness is that oxygen will combine with your metal and break it down. The red sands of Mars are all made from oxygen binding with iron to form iron oxide. Rust. When we mix nickel and chromium, we get an alloy that forms a top layer of oxide like the one that forms on stainless steel and aluminum. This is called a passivating oxide layer, which means an inert layer of substance over a metal that protects it from corrosion. Inconel has amazing strength and is resistant to high temperatures that would weaken any other metal to the point of failure. It is important to realize that the usefulness of any metal is determined by the application you have for it. Aluminum is great for airplanes, but can't handle the heat of re-entry for a spaceship without a lot of shielding, which means added mass. A metal might not melt at a very high temperature, like wrought iron, but becomes so flexible that it can't hold its shape. We are almost certainly not going to discover new elements out in space, unless there is an island of stability for transuranic elements, which no one has seen any sign of so far. But we will have access to rare metals that could make alloys much better than anything we have now. Inconel comes in many suballoys for different applications. It was first developed in the 1940s in England as the British were trying to create the first jet engines. They had quickly found that the extreme heat and stress of a jet turbine engine destroyed even the strongest steel. They kept coming up against a problem called creep. Many of us have experienced a creep, but this is different. Creep describes the tendency of a solid material to deform slowly and permanently under continuous mechanical stress. Think of spinning a propeller made of soft plastic. It would quickly start to stretch out from centrifugal forces. As the blades of a turbine spin at very high speeds, the blade material will also start to experience enormous g-forces, and this will change the shape of the blade. Steel is only good up to about 500 centigrade. Then it becomes too soft and starts to deform. Something else was needed. The scientists in Sheffield, England, you will remember, had developed an alloy of iron that we call stainless steel. They also developed Inconel to help Sir Frank Whittle design his turbine engine. And they are still innovating today. They turned to nickel alloys to overcome the limitations of steel. Nickel doesn't melt until it reaches 1455 centigrade and seemed a good starting point. It is also very resistant to corrosion. You don't see rust on nickel coins in circulation around the world. Nickel easily forms alloys, as we saw when it combined with iron and meteorites to form a natural alloy. Steel and even titanium start to rapidly lose their strength at only 40% of their melting temperature. Nickel alloys stay strong at up to 85% of its melting temperature. The gases from the combustion chamber of a jet engine are at 1,700 centigrade, and the high-pressure shaft spins at up to 12,000 RPM. To keep even Inconel from melting, the blades are cooled by coating them with a low-heat conductive ceramic and have internal channels through which cooler air is routed. Much as fuel is circulated around the nozzle and combustion chamber of a modern rocket engine to prevent overheating. This cooling air is around 650 centigrade, but that is well below the melting point of this nickel alloy, and it forms a sheath of cool air around the blade. This keeps the blade temperature in these engines at around 1150 centigrade. They can easily handle this. Modern jet engines are one of the most refined and dependable machines ever built by humans. Now, crystals form as alloys go from molten to solid. These crystals are just tens of microns across and are randomly oriented. At high temperature and stress, these crystals start to slide against each other, and any impurities create weak points between crystals. This is what causes creep. The engineers and metallurgists soon started finding ways to make all the crystals line up in one direction, with their long axis in line with the stress. Other alloys of nickel are possible also. Rolls-Royce has funded the development of single crystal metal alloy blades for their turbines. This means that the entire turbine blade is cast in such a way that it is all one crystal and there are no boundary layers. When nickel crystallizes, it forms a face-centered cubic shape, just like our austenitic steel from our last lesson. This shape has 5 atoms, one in each corner of the cube and one in the middle of it. Rolls-Royce has found that if they add a little aluminum to their nickel and chromium alloy, that also contains small amounts of titanium and tantalum, they can produce a precipitate crystal with aluminum at the corners and nickel in the center that helps to order the other crystal precipitates and can form a single solid crystal without boundary layers. The process to do this is extremely complicated. They first make a ceramic core that has the internal cooling channels in place. They inject wax to form the shape of the blade. Platinum pins are inserted to support the core inside the wax. Then the form is coated with a mixture of aluminum silicate to form a ceramic coat. Several more coats are applied, and then the wax is melted out, leaving room for the alloy. The ceramic mold is then heated in a furnace, and molten alloy is poured in through a helical structure to spin the molten alloy for even distribution. The mold is filled and the alloy hardens. The ceramic mold is dissolved in a caustic alkali solution. Holes for the cooling air are precisely drilled out with electrical discharge machining. Then electron beam plasma deposition is used to apply the insulating ceramic coating over the single crystal alloy blade. I go through this process in detail because you need to understand that this technology is vital to the reusability of rocket engines. One of the limits of rocket reusability has been the turbopump blades. The Raptor engine has been designed for complete reusability. This is a full-flow staged combustion engine with 2 turbopumps. There are 2 pre-burners, one where a little bit of fuel is burned with a lot of oxygen, called the oxygen-rich side, and the other where a lot of fuel is burned with a little oxygen, called the fuel-rich side. On both sides you get heat and combustion, but the exhaust of one is still mostly oxygen and the other mostly fuel. The exhaust is fed over a turbine, just like in a jet engine, and the turbine spins up to speed. The turbines are attached to pumps, and as you can see in this diagram, all of the fuel is pumped through the fuel-rich preburner and turbopump, while all of the oxygen is pumped through the oxygen-rich preburner and turbopump. The blades on these turbopumps have survived the extreme heat and shock of startup, as well as the incredible stress of operation. In disposable rocket engines, the blades must only survive for a few minutes. In the Raptor engine powering the Starship, they will need to operate for hundreds if not thousands of flights, just like the Rolls-Royce jet engines that let us fly so safely today. Inconel was used for the skin of the X-15 rocket plane so it could survive the suborbital re-entry heat and high speeds of flight. The thrust chamber of the F-1 rocket engine on the Saturn V was made of Inconel. The space shuttle was held to the launch platform with 8 Inconel studs that could support its entire weight and were explosively cut for launch. The Merlin engine on the Falcon 9 is made of Inconel, and the Super Draco rocket engines on the Dragon crew capsule are 3D printed out of Inconel. Nickel and chromium-based alloys used in these applications, and in the Raptor turbopump blades, are the only alloy capable of surviving the high-temperature, high-oxygen environment on the oxygen-rich side of the Raptor engine. Elon Musk tweeted 22 December of 2018 that the SpaceX metallurgy team had developed a superalloy of Inconel called SX500 that could survive the 12,000 pounds per square inch of pressure, high temperature, and oxygen-rich gas that would cut through the best steel like a plasma torch. The engine manifold of the Raptor engine will be made from this Inconel alloy also. Here you can see one being cast. A mastery of metallurgy is one of the most innovative areas of expertise that SpaceX has developed and allows them to create machines capable of doing things no other company can match. Other companies are trying though. Rocket Lab out of New Zealand also uses Inconel in their Rutherford engine seen here. 9 of these small engines power the beautiful carbon fiber Electron rocket made at their factory. These engines are manufactured by putting Inconel and titanium powder through a 3D printer that uses laser and electron beam sintering to create all the primary components, including the engine chamber, injectors, pumps, and main propellant valves. Being able to print these amazing superalloys will be a vital part of the space industry in the future. You cannot take a foundry with you to an asteroid when you go mining. You can, however, have a good 3D printer on your ship and print yourself a massive cargo hauler with several efficient rocket engines to get your mined precious metals and volatiles to where they are needed. The company Relativity Space has been the most innovative in this field. This is a good example of why so many areas of technology and science will be revolutionized by space exploration and colonization. Relativity Space has learned from SpaceX's example. It is deploying its own alloys, electronics, and remarkably, it has built incredibly huge 3D printers with the goal of printing a complete rocket from top to bottom. Here you can see their printers producing a rocket propellant tank. What normally takes years can be reduced to days. They are designing and starting to print their own rocket engines called Eon for use in an almost completely 3D printed rocket they will call Terran 1. This rocket will use liquid methane and oxygen just like the Starship, and it will have 9 engines, just like the Electron rocket by Rocket Lab and the Falcon 9 by SpaceX. This type of innovation that has been inspired by the success of SpaceX is what my friends Sebastian and Shishwan over at To the Future call disruptive technology. Disruptive technologies change everything about an industry. Finally, I will speak for a moment about the importance of access to rare earth elements and precious metals. I have often stressed the importance of our civilization having access to these materials, not to sell them on the open market. The gold and platinum market will crash when the first mining ship lands on a metallic asteroid, but for what we can make from these metals. If you look at this graphic, you will see that metal most resistant to salt corrosion today is not a superalloy, but platinum. If platinum were not so expensive, we could have more efficient catalysts for fuel cells and pollution removal. We could have desalination plants in oceans around the world, pumping fresh water into our cities, and not have to destroy our rivers and the wildlife and farmers that depend on them. Scientists at Rice University were searching for a good metal for artificial hips and other joints. Cobalt steel had been used, but the cobalt would dissolve into the surrounding tissues and cause heavy metal poisoning, and the joint would have to be removed. Titanium has been used since it is exceptionally light and strong. The scientists discovered, however, that an alloy of titanium and gold, which I will call Titaurium because it sounds so cool, was 3 to 4 times harder than the best steels. Now remember from the lesson on Starship Steel that hardness is resistance to abrasion and strength is resistance to deformation. Something can be hard but brittle, like diamonds or tungsten, or strong but soft, like aluminum and magnesium. For an artificial joint, you need strength and hardness. You don't want the joint to wear out or put metal fragments into the tissues. The scientists found that a 3-to-1 mixture of titanium and gold created this atomic structure. Look familiar? That is 4 times harder than pure titanium and could be great for this and other purposes. Strange things happen with alloys. Scientists found that, while both titanium and gold are not magnetic, a 1-to-1 alloy of these was. It was also found that if you mix titanium with gold at an extremely high temperature, it will form a beta version of its crystal when it cools. This beta crystal gives the alloy its extreme hardness. If it is heated to a lower temperature, it will form alpha-type crystals when it cools, and be no harder than regular titanium. These discoveries were confirmed by scientists at other labs in Texas and Florida. Superalloys can only be developed if we have access to rare and precious metals in quantities and at a cost that allow us to discover these amazing materials. Thanks for listening. Please like and subscribe and support us on Patreon at patreon.com/Terran Space Academy if you can, so we can continue to educate you on what you need to know to have a bright future in the space industry. At Astra Pro Terra, stay safe.